Hello, welcome to my video series of algorithms. This is part 13 of Module 1, Sorting Algorithms. In this video, we will continue discussing the external sorting algorithm. We will present the polyphase merge technique that can further improve external sorting. Recall the naive external sorting algorithm and the multi-way merge strategy we have presented in the previous video. We see that to perform a k-way merge, we need to use two k-heads. However, the hard disk may not have that many physical magnetic heads available, in which case may incur additional overhead. To address this issue, here we present the polyphase merge strategy, which can reduce the number of heads from 2k to k plus 1. To understand the intuition behind polyphase merge, consider the naive two-way merge strategy. Theoretically, we only need 3 heads, where 2 are used as inputs and 1 is used to write the output. However, we used 4 heads when implementing the algorithm. This is because after merging 2 arrays into one, the sole array has no partner to merge with in the next phase. Therefore, we need to write outputs to 2 arrays, such that in the next phase, we still have 2 arrays to merge. So, our goal becomes finding a partner for the output array such that they can be merged in the next merging phase. And we have to do that with only 3 heads. The solution is simple. We can write different numbers of data blocks to the input arrays A1 and A2. Say we write more blocks to A1 than A2. Since the merge phase consumes the same number of data blocks from A1 and A2, A1 will still hold some data blocks after the merge phase. A1 can thus serve as the partner of the output array A3 and together be merged in the next merge phase. Of course, each data block in A1 may contain fewer elements than that in A3. Luckily, the merge procedure will work even if the 2 input data blocks have unequal sizes. Consider the same example we had in the previous video. Now, we will use only 3 heads, A1, A2, and A3. Again, we assume that we only have space to hold 2 data elements at a time. Therefore, we begin with loading 2 elements in memory, sorting them internally, and writing them to the external arrays A1 and A2. Note that the arrays A1, A2, and A3 are all stored in the hard disk. We have unequal numbers of blocks in A1 and A2, where A1 holds 3 blocks and A2 holds 2 blocks. We then begin the first merge phase. We merge the first blocks in A1 and A2 and write the merged list to A3. We then merge the second blocks in A1 and A2 and append a merged list to A3. Recall that we defined the above process as a single merging phase, characterized by sequential reads of the input arrays and a sequential write to the output array. We also say that the merge phase consumes 2 data blocks from A1 and 2 data blocks from A2. It also writes 2 data blocks to the output array A3. Pay attention to the number of data blocks consumed and the array that serves as the output. Together, they will make 2 very important observations that will be summarized after discussing the example. At this point, A1 holds 1 data block and A3 holds 2. Recall that without polyphase merge, we will proceed with merging the remaining data block in A1 with an empty block and append the merged block to A3 as its third data block. However, with polyphase merge, we will terminate the current merge phase and start merging data blocks in A1 with those in A3. Note that we don't need to shift the head A1 to a different location, since the data access pattern remains sequential. Here, we merge the remaining data block in A1 with the first data block in A3. We write the merged list to A2. The above process corresponds to the second merge phase. And in this phase, it consumes 1 data block from A1 and 1 data block from A3. it writes one data block to the output array A2. Now, A2 contains one data block and A3 contains one data block. We enter a new merging phase and merge these two data blocks. In the last merge phase, we consumed one data block from A2 and one data block from A3. We also write one data block to the output array A1. At this point, we are done with the sorting. With the above example, we have shown how to perform external sorting with only k+1 heads. The trick is to write different numbers of data blocks to the input arrays. We can also make two important observations. First, the number of data blocks consumed at different merge phases is also different. For example, we consumed 2, 1, and 1 data block from each input array at the 3 merge phases. Second, the external arrays take turns to serve as the output array. For example, A3, A2, and A1 served as the output array for the 3 merge phases, respectively. At this point, two important questions remain unsolved. First, since the number of data blocks is distributed to the external arrays unevenly, how many data blocks should we write to each external array to begin with? Second, since different merge phases consume different numbers of data blocks, how to determine the number of data blocks to consume at each phase? To answer both questions, again consider the simple two-way merge. Say we have access to 3 external arrays, A1, A2, and A3. Also, denote the number of blocks that are merged from each array at the ith phase as Mi. Recall that the external arrays take turns to serve as the output array. That is, if A3 has served as the output array in the ith merge phase, A2 and A1 will serve as the output array for the I+1th and the I+2th phases. Here, the first figure shows the snapshot after the ith merge phase, where A3 serves as the output array and Mi data blocks were written to A3. Since A3 is empty before serving as the output array, it will contain exactly Mi data blocks after the merge. In the I+1th phase, we need to consume Mi+1 blocks. Since A2 needs to be empty and serve as the output array in the I+2th phase, all blocks containing A2 must be consumed in the I+1th phase. Therefore, we can infer A2 contains Mi+1 blocks at the end of phase I. Now, consider the second figure. In phase I+1, Mi+1 data blocks are consumed from both A2 and A3, and Mi+1 data blocks are written to A1. For a similar reason, A3 needs to be empty and serve as the output array in the phase I+3. Therefore, all data blocks containing A3 must be consumed in phase I+2. Then, let's look at the third figure. In phase I+2, Mi+2 data blocks are consumed from both A1 and A3, and Mi+2 data blocks are written to A2. You can see that after phase I+2, A3 becomes empty again. If we set our focus to A3, it contains Mi blocks at the beginning. In the two subsequent phases consumed Mi+1 and Mi+2 data blocks, respectively. And after that, it becomes empty. In this case, we can easily summarize that Mi equals to Mi+1 plus Mi+2. Consider the relation. It quickly reminds us of the Fibonacci series. The only difference is that the Fibonacci series is an infinite increasing series, while we are dealing with a finite decreasing series here. It means that we need to find a proper starting point for our series, but otherwise, it is identical to the Fibonacci series. With the relation, now we can answer the two unsolved questions. First, let's see how many data blocks should we write to each of the external arrays at the beginning. It also means finding a proper starting point for our number series. If you reconsider the example we had before, you can see that at any phase, the numbers of data blocks stored at the two non-empty arrays always correspond to the two adjacent Fibonacci numbers. It means that we can simply distribute the data blocks according to this rule. Now, let's figure out the starting point of the series. The simple rule is that if we have n data blocks, we shall find the two smallest adjacent Fibonacci numbers whose sum is larger than n. For example, if we have 16 blocks, we should pick the two adjacent Fibonacci numbers 8 and 13. It means that we can write 8 blocks to one array and 13 to another, totaling to 21 blocks. While we only have 16 blocks, we can pad dummy blocks to make the total number of blocks become 21. Even better, we can implement a smart mechanism to detect the exhaustion of data blocks and pre-terminate the program. What we have discussed above is for the application of polyphase merge to two-way merge. Next, we will extend the discussion to k-way merge. First, we can naturally extend the relation among the number of data blocks consumed from each external array to the kth order Fibonacci series. This is because each external array now needs to serve as input array for k times before it serves as the output array again. Therefore, the number of data blocks that are written to the array should equal to the sum of consumed data blocks of the k subsequent merge phases. In other words, the next number in the series is the sum of the k numbers before it in the series. This is exactly the definition of the kth order Fibonacci number. Please see the formula shown in the slides for its formal definition. With the kth order Fibonacci series, it is tempting to extend our conclusions drawn from the two-way merge case. That is, the number of data blocks consumed from each external array should correspond to the kth order Fibonacci series. And we should initiate the polyphase merge by distributing the data blocks among k external arrays based on the kth order Fibonacci series. The first conjecture is correct. However, the second conjecture is wrong. And we will have to find the correct way to distribute data blocks among the external arrays at the beginning. To see why the second conjecture is wrong and what would be the correct way to distribute data blocks, let's consider an example of the five-way merge. Here we have a table to record the number of blocks stored at the 6 external arrays, A1 through A6, at different merge phases. Each row corresponds to an external array, and each column corresponds to a merge phase. Note that we require 6 external arrays to perform a 5-way merge because we need one additional array to serve as the output. Let's take the first column to represent the number of data blocks stored among the arrays after the last merge phase. We don't know how many merge phases we need. Therefore, we will say that the last merge phase is the zth phase. Since the last merge phase must produce the final result, all elements to be sorted must be written to one array as a single data block. Without loss of generality, let's say the only data block is written to A6. None of the other arrays should contain any data. So, A1 through A5 should contain 0 data blocks. We know that the number of data blocks consumed from each input array should equal to the number of data blocks written to the output array. We know that the zth merge phase consumed one data block from each input array. In other words, it took one block from A1, one from A2, and so on, merged them into one block, and wrote to A6. Since A1 through A5 contain 0 blocks after the zth phase, and the zth phase consumed one block from each of them, they must contain one data block before the zth phase. While A6 serves as the output for the zth merge phase, it must contain no data block before the zth merge phase. Taken together, we can infer the number of data blocks stored in each external array before the zth merge phase, or after the z-1th merge phase. That is, A1 through A5 should each contain one data block, and A6 should contain 0 blocks. Then, let's, based on the data block distribution after the z-1th merge phase, infer the scenario before the z-1th merge phase. Since A6 served as the output for the zth merge phase, A5 should serve as the output for the z-1th merge phase. Since A5 contains one data block after the z-1th merge phase, it means that the z-1th merge phase consumes one data block from each of the other arrays. Therefore, we should add one block back to each input array when inferring the data block distribution before the z-1th merge phase. It means that we should add 1 to all arrays except the output A5, which should contain 0 data blocks before the z-1th merge phase. With the same logic, we can infer the data block distribution before the z-2th merge phase, before the z-3rd merge phase, before the z-4th merge phase, before the z-5th merge phase, and finally before the z-6th merge phase. If you look at the numbers below the dashed arrows at the bottom of the table, they correspond to the 5th order Fibonacci series. These numbers are the numbers of data blocks consumed from each input array at the corresponding merge phases. However, if you look at the numbers of data blocks stored in arrays, not all of them correspond to the 5th order Fibonacci series. Since the numbers at each column directly tell us how to distribute the data blocks, we would like to find some patterns from the example. Take the last column, for example. We realize that the largest number in the column is the sum of the last 5 numbers of the 5th order Fibonacci series. This is expected as the array will serve as an input array for the next 5 merge phases. So, the number of blocks it contains must be equal to the total blocks consumed in the next 5 merge phases. Similarly, if we look at the second largest number in the last column, we realize that it is the sum of the last 4 numbers of the 5th order Fibonacci series. This is also because the array will serve as an input array for the next 4 merge phases. You can verify this pattern for the rest of the numbers in the last column. The third largest number is the sum of the last 3 numbers of the 5th order Fibonacci series. The fourth largest number is the sum of the last 2 numbers of the series. The smallest number is the last number of the series. Here is a more formal summary of the pattern we have learned from the prior example. While the pattern is easy to summarize, we will need to define the parameter I that can help us locate the numbers in the z-ith column. To find I, first know that the numbers in each column are independent of the input data set. They are only determined by the kth order Fibonacci series. Therefore, those numbers can be precomputed for a given order k and phase I. For a given input case with n data blocks, we can simply search in the precomputed table until we find the smallest I such that the sum of all numbers in the ith column is larger than n. For example, if we have 45 data blocks in total, we can search the table from left to right. We find that in the z-5th column, all numbers add up to 55, which is larger than 45. We cannot take the z-4th column, as all numbers in it add up to 33, which is smaller than 45. In this case, we know that we can distribute the 45 blocks based on the numbers given in the z-5th column. Know that the 45 blocks we have are less than 55 indicated in the z-5th column. Similar to the two-way merge case, we might need to pad empty blocks or implement a smart checking mechanism before distributing the data blocks. In summary, we have discussed the polyphase merge technique for external sorting. The goal of polyphase merge is to reduce the number of external arrays that are being accessed simultaneously. In other words, the number of heads in use. We have shown the details of polyphase merge and discussed its relation with the Fibonacci series for both the two-way merge case and the more general k-way merge cases. In the next video, we will discuss the last external sorting technique, replacement selection. Thank you for watching and see you next time.